Hi there, everybody. This is a very impromptu video here. I know that this is probably not the prettiest example of this, and a lot of people could do a lot better, but my intention here is to sort of start to sort out the idea in my own head of what statistical power is all about. Okay, so here's our situation. Suppose that we believe that the average height of people is 100 units, and somehow, this is sort of unrealistic assumption, but somehow we know that the standard deviation of heights is like 10 units. Okay, so the idea is we're going to sample 100 people and we're going to do a significance test of the null hypothesis that mu is in fact 100. Okay, so maybe I don't even need this here. But like, suppose that in reality the mean height is actually 102. So the question is, like, what is the power of our test to detect this alternative? So the way I like to visualize this is just to show the distributions of the sample mean. First of all, obviously if we're drawing 100 people, if sigma for the population was equal to 10, then sigma for x bar will be equal to 10 over root 100, which is 1. Okay. So let's just like take a look at these two distributions. So this is like what we think is happening. And then this guy in the red represents the actual distribution of sample means that we should be observing. Okay, so the idea here is we're doing our test as if this null hypothesis here is true. In which case, we're going to be rejecting our null hypothesis if our sample mean is anything more than 102, and we're going to be rejecting it if it's anything less than 98. This is, I'm sort of like ballparking, saying that at the 95% significance level is close to a Z score, or a Z critical of mu plus or minus 2 sigma. So like, if we take a look at both of these distributions on the same graph, we can see that, okay, if in reality this thing is happening, we think this thing is happening, like what region, like where does the rejection region under the null hypothesis coincide with the actual distribution that's happening? Okay, so I think I've done an okay job of sort of drawing that here. Basically, if you're outside of 102 to 98, we're going to reject. And so where that overlaps the real distribution of sample means of height is out here and over here. So I've said, like, if our sample mean that we draw is anywhere in the red zone, we're going to reject the null hypothesis, and we're going to be correct in doing so. However, if, let's say, we grab a sample mean and it ends up being like 100 or 101, well, in that case, since we're still in the acceptance region for under the null hypothesis, we're going to sort of naively continue believing the null hypothesis, even though it's not in fact true. So this points to the power of our test to detect the alternative, that in fact mu is 102. So what I've done is I've popped into R to give us this probability. So what I've reasoned is that the probability of being 98 or less, given that mu is 102, plus the probability of being, so this is 1 minus the probability of being less than 102, given mu is 102, is the same as being greater. And so, sort of predictably, since there was a fleetingly small amount of density to the, less than 98, that contributes almost nothing. And in this case, there was coincidence between the rejection range of the first distribution and the mean, or the 50% mark, of the second distribution. So, but we can imagine a case where, let's say we wanted to get the power of our test to detect the alternative that mu is in fact 103. Well, all we would do is change to 103. Right here. Now note I left 102 here because the rejection range under the null hypothesis is still the same. So then the power of our test to detect that alternative bumps up to 84%, which means our probability of a type 2 error would be 1 minus that, or about 16%. What would be the power of our test to detect the alternative that mu is 104? It's starting to get very, very good. And if we take mu to be 105, I mean, it's almost 100%. Okay, so sorry about the really sort of shoddy explanation there. Again, as I said, I'm like working on trying to understand this myself, and certainly my notation for what was happening here wasn't really very clean. But I hope that the overall concept here, that if you want to know the power of your test to detect an alternative, you can simply sketch the distributions of your under your null hypothesis and under your alternative hypothesis. You can see where the rejection region under the null hypothesis overlaps the distribution of what's happening in reality, the alternative, and then you can use computer software to give you the actual probabilities of the zone of overlap. Okay, thank you very much.